Hello, this is lesson number 2 in chapter 13. We're picking up in the same presentation, and that is at slide number 15. Okay, here's another term for you, basic size. That's the dimension to which tolerances are applied. Now, strength, deflection, performance of a part determines the nominal minimal size of the part. Okay, so the basic size is chosen from lists of preferred basic sizes. In our case, that's in Appendix 2, Table A2-1 on page 784. That is our table of basic preferred sizes. Okay, let's talk about clearance fits now. Okay, in a clearance fit, there has to be motion between two mating parts. Okay, that's like a bearing and a pin. Okay, there has to be movement between it. Okay, so when there must always be a clearance between mating parts, you're going to want a clearance fit. So the designation for standard clearance fits, that's shown in ASME Standard B 4.19 classes. That would be RC1, which is a close sliding fit, through RC9, which is a loose running fit. Now, in Brightspace, I've given you a table from B 4.1 so you can see these fits. The table looks like something like this. Okay, so we have the basic or nominal size here, and that's printed as a range. And then for each one of the fits, you got RC2, RC5, and RC8. You have 3 columns. The first one would be the limits of clearance. That would be the minimum clearance, in this case 0.01, and the minimum clearance is also called the allowance, and then 0.55 for the maximum clearance. And then based on what the basic hole is, okay, what the hole size is, here's your tolerance for the hole, and then here's your tolerance for the shaft. Now these are going to be in units of 1/1000th of an inch. We're going to talk about that in the third lesson. And then here's clearance fits for our C2, 5, and 8. Okay, let's talk about basic hole system. So the hole is, the fit is designed on the basic hole size of the hole. Okay, so the hole becomes the basis at which the tolerance are applied. And then the allowance is applied to the shaft. The basic size is always the minimum hole size. And how can we tell that? It's like, here is the hole, it's 0. Okay, so that's how you know this is a basic hole system chart. Here's a graph you've seen before. And really what this is, it talks about the different fits for the running clearances. Okay, so it starts here at RC1 and it goes up to RC9. Now look what you got here on the right side column. Okay, so the length of these bars is the tolerance. Okay, so this is the tolerance of the shaft, and up here you have the tolerance of the hole. Okay, and then the distance in between these bars is the minimum clearance, or the allowance. Now the distance from the bottom of this one all the way to the top, now that would be the maximum clearance. Now as you can see, as we're talking here at RC1, everything's a lot tighter, your allowances are tighter, your tolerances are tighter, and then as you start moving up into RC9, you have a lot more allowance, you have a lot more tolerances, you got a lot more sloppier of a fit. So that's how you look at this particular chart. Now interference fits are different. Okay, in an interference fit, the shaft is always bigger than the hole. Okay, and you want to put these parts together such that they stay together. Now there are different classes of these interference fits. One would be called a force fit. So that's where you're controlling the pressure between the mating parts throughout the size range. That means that you're forcing these parts to go together. Now, to differentiate between that and a shrink fit is when you actually have to heat up the hole, the part that has the hole, and maybe even freeze the part that has the shaft, so you can use the coefficient of thermal expansion and then put the parts together, and then when they heat up to room temperature, then they're stuck together. Okay, so there's 5 classes, FN1 through FN5. And again, the tables are set up very similarly to the clearance fits. So these were there. And then we have transitional fits. That's where you got accuracy of location is important, but you really don't care if there's a little bit of clearance or a little bit of interference. That's where you would use a transition fit. And I got a couple of slides in general tolerancing methods. First of all, you establish tolerances on each dimension of each component in mechanical design. Tolerances must assure that the component fills its function. And they should be as large as practical, because when we showed you the charts, as you start making the tolerances really tight, your costs go way up. And then if you take some other classes with me, you'll talk about geometric dimensioning and tolerancing. And then there's another term called surface finish. And when you're putting two parts together, you really need to make sure that you have a nice surface finish, because in a lot of cases the roughness of the parts would prohibit them from moving. So this is the end of lesson 2.